So today we will discuss something called inner product space. Okay. So what is inner product space? So we already know what is a vector space, right? In vector space, if we have some additional properties, then we call that as a inner product space. So what are those additional properties? So say we have that's a vector space. Let's say that's a vector space, and in that vector space, say I take two vectors. Okay, so let's say one vector is u, another vector is v. Okay, so somehow I combine these two vectors. Okay, um, so I'll put it in some function f, which is going to be a function of u and v, and then this function will give a scalar value. Okay, let's say that scalar value is say alpha. Okay, so for example it could be in a real space. Okay, then such a function can be called as inner product. Okay, and still in order to say that that's an inner product and inner product space, so the same vector space can be called as inner product space along with this function, provided if this function satisfies two properties. Okay, so let's denote this function like this, just a bracket of u comma v. Okay, so that should be equal to v comma u. So this product, even if I exchange u and v, the result should be same. Okay, so that's one thing. The other thing is alpha u plus beta v. So that's a vector. So u and v are a vector, so it's a linear combination of those two vectors, right? And if I do the inner product with the new vector, let's say w, and that is same as alpha u comma w plus beta v comma w. Okay, so that's another property. And then a third property, say I take u and again I take u. Okay, and if I do this inner product, it should be greater than or equal to 0. If these three things are satisfied, then I could say that it's an inner product, a proper inner product, and the vector space is nothing but an inner product space. Okay, fine. Let's see some examples. Um, so in Rn vector space in R3 or R2, you know something called a dot product, right? So the dot product is an inner product for that R3 space or Rn space in general. Okay, so could you check whether these properties are being satisfied in that Rn space? So vector u can be written as like u1, u2, dot 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 un, right? And v can be written as v1, v2, dot 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 vn. Okay, if you assume that where u1, u2 or v1, v2 can take any real value. Now what about the first property? Okay, so how do you take the dot product for this vector, for these vectors? The first element into first element plus second element into second plus third into third, like that. Okay, so what about the first property? Do they commute? Yes, they commute. Okay, fine. What about this one, the second one? So for example, the first element is alpha into u1 plus beta into v1. Yeah, so it satisfies, right? What about the third one? Will it always be positive or equal to 0? So it will be like u1 square plus u2 square plus u3 square, right? So always positive. And when it will be 0? If one of sorry, so if u vector is a 0 vector, only then it will have an equal to 0. Okay, otherwise it will be greater than 0. We will see that as a magnitude of the vector, right? So that's what it's a magnitude of the vector. Okay, fine. Now that's okay for R in space. Now we have also discussed that all functions is a vector space, right? So in that case, is there any function which I can come up with so that it satisfies all these three properties? Okay, yeah. So that I could call that as an inner product space. Okay, so for that. There is a function, let's say some u and v, or let's say the function, uh, the space. Okay, let's say this contains the entire real valued functions. Okay, so we already know that that's a vector space. Now let's say we'll take one function called f of x, another function g of x. Okay, now, the inner product is going to be defined in the following manner. Integral, let's say between some interval a to b, okay, um, f of x into g of x dx. Okay, I'm just going to define it like this. Now, um, just tell me whether these properties are being satisfied for this case. So what about the first one? If I interchange f of x and g of x, it will be same. No issues. Okay, the first one is okay. What about the second one? So what is it? Integral, say a to b alpha f of x plus beta g of x, the whole into, let's say, h of x, okay, dx is equal to integral a to b alpha f of x h of x plus integral a to b beta g of x h of x, right? And dx has to be put here and here. Okay, and this is same as alpha, uh, yeah, alpha into, I can take alpha outside, so which is same as the inner product of f and g, and here the inner product of g and h, sorry, f and h and g and h, right? So this property also gets satisfied. What about the third one? So f of x getting in a product with f of x itself, will it always be positive except when f of x is 0? Because f of x into f of x square, so it will always be positive. So f of x could be either positive or negative. So x square will, f of x square will be always positive. So if it's always positive, the integration of that thing will also be positive. Okay, so this also satisfies. Then I could say for some interval, okay, a to b, if I define this as the inner product, then these properties are satisfied, so this is a inner product space. And also for a given function I could now I could say something called magnitude of that function. Yes.
If f of x is minus sin x.
Say if f of x is minus sin x, okay. Say minus f of x is equal to minus sin x, okay. Now what's your doubt?
Third property.
Third property, okay. Let's say integral from minus, let's say a simple 0 to pi by 2. Okay, fine. So minus into minus plus, so it's like sine square x dx, right? So if you plot sine square x, what you will get between 0 to, so the sine x is like this between 0 to, no, sine x is like something like this up to here, right? So this entire thing is positive. Sine square x, sorry, that's sine x. Sine square x is also positive, maybe something like this. I don't know, because this entire value will be less than 1. So maybe something like this, I don't know. Okay. So still, if we calculate the area under that curve, it's positive, right? So even though the function is minus sin x, right? So if you do the same for a different interval, let's say for the interval where the sin x will go to negative, say pi to 3 pi by 2, okay. So how does it go? This part, right? So but still it will be positive, right? So third property will satisfy.
So for if interval is negative.
Even if interval is negative, doesn't matter. So you can choose any interval. See, the thing is, yeah.
Yes.
So
Minus pi by 2 to 0.
minus pi by 2 to 0. Okay, let's check. Mm, so how does it look? Okay, so this is minus pi by 2 to 0. So which means here to here.
Yes.
Okay, but when I do a square, sine square, so what is the sine square between that interval? It is positive, right? So it will be something like this, I don't know, right? So once again you will get a positive value, area under the curve is positive. Okay, so that's the inner product, okay.